Now we have a 6 kilogram object moving to the right at 12 meters per second, 15 kilogram object moving at negative 8 meters per second, meaning it's moving to the left. These are the same masses and velocities we used in the preceding problem. And just before collision, these are the velocities and masses. During the collision, well, the masses are in collision. They come together, they kind of compress, and then they spring apart. And they look a little crumpled here, but they're going to spring back to their natural shape immediately after collision. But during the collision, they're crumpled up and exerting elastic forces on one another, some inelastic forces also. And during the collision, which lasts for delta t equals 0.03 seconds, they're therefore exerting equal and opposite forces on one another. F12 being the force exerted on object 1 by object 2, F21 being the equal and opposite force exerted on object 2 by object 1. The two masses then, after springing apart, end up with their velocities after collision, immediately after the collision. Now we don't care what happens any time after this. After this, these things might collide with something else. They might slow with friction. A lot of things might happen, but we're just talking about immediately before, during, and immediately after the collision here. The first object rebounds with a velocity of negative 5 meters per second, moving to the left then. The second will have an unknown velocity, which we'll call v2 prime, and that's what we're trying to find. So that if this first object with this velocity collides with the second at this velocity, the collision takes 0.03 seconds, then the first object springs away at negative 5 meters per second. What is the velocity of the second object? Okay, now we're going to do analysis of this in 3 different ways. We'll start with an analysis that actually calculates average forces and the effects of those average forces. Okay, first of all, I have a delta on this P1 and it doesn't belong there, so let me just obliterate that. Unfortunately, this state bid whiteout here also obliterated part of my equal sign, but hopefully you can still see that that's an equal sign. Okay, the original momentum is I'm sorry, the delta should have been there. This is the change in momentum of the first object. I wrote these a little while ago and just messed up a little bit. As soon as the whiteout dries, I'll put the delta back in. But our delta P1 is the final momentum minus the initial momentum of object 1. The final momentum is the negative 5 meters per second times the 6 kilograms. The initial is the 6 kilograms times its original 12 meters per second. So the momentum change is negative 102 kilogram meters per second. Since delta t is 0.03 seconds, we can then conclude that the force exerted on object 1 by object 2, and this should be the average force, so let me put a bar over that to indicate average, is the change in momentum divided by the time interval. When we divide the negative 102 kilogram meter per second momentum change by the 0.03 second time interval, we get negative 3,400 newtons. Okay? Whiteout isn't quite dry, so I can't change that yet. And then, since the force exerted on object 2 by object 1 is equal and opposite to the force exerted by object 1 on object 1 by object 2, the force on object 2 is plus 3,400 newtons. So that the acceleration of object 2 has to be 3,400 newtons over 15 kilograms or 227 meters per second, which over a 0.03 second time interval gives us a change in velocity of 6.8 meters per second. So that the final velocity, v2 prime of the second object, is the initial velocity plus the change in velocity, negative 8 meters per second plus 6.8 meters per second, or negative 1.2 meters per second. Now notice that when I drew the arrow on the first object, I had the arrow pointing to the right, assuming that the first object would move off to the right after collision since the second object rebounds to the left. My assumption was wrong, but that doesn't matter because I got a negative when I solved for v2 prime. So I'm going to have to reverse that arrow if I want this to be right, but I still have the correct velocity after collision. My assumption of direction has no effect on the actual result. An alternative solution is to note that the forces are again equal and opposite, and we'll do the average forces, so that the impulses are equal and opposite, because we get the impulses by simply multiplying the average forces, which are equal and opposite, by the same delta t. The equal and opposite forces acting for the same time interval give us equal and opposite impulses, so equal and opposite changes in momentum. Now, we then conclude that delta m1v1 is a negative of delta m2v2. Since m1 and m2 are constant, the change in m1v2 is just m1 times the change in v1. Similarly, over here we get m2 times the change in v2. So these are equal and opposite, which tells us that delta v2 is, dividing through by m1, negative m2 over m1 times delta v1. And now we simply substitute the 6 kilograms and 15 kilograms for the two masses. And the I've got the subscripts wrong here. That should be m1, and this should be m2. 6 kilograms being mass 1, 15 kilograms being mass 2. The delta v1 is the negative 5 meter per second final velocity minus the 12 meter per second initial velocity. The ratio 6 over 15 is 0.4, and that should be negative 0.4, times negative 17 meters per second, the change in velocity of the first object. So the second object has a change that's 4/10 of the change in the first and of opposite sign, giving us a change of 6.8 meters per second. And we then conclude that v2 prime is v1 prime plus delta v. That should be v2 plus delta v2 must have been later than I thought it was when I wrote these. And that gives us again our negative 1.2 meters per second, using the negative 8 meters per second of the first object and its change 6.8 meters per second. That's the second object. Okay? And one more alternative solution. Since a change in momentum, the change in m1v1 plus m2v2 is 0, and m1 and m2 are constant, we conclude that the initial momentum, m1v1 plus m2v2, is equal to the final momentum, m1v1 prime plus m2v2 prime. Since the momentum isn't changing from before to after, this has to be the case. And we note that we know the mass is m1 and m2, so we underline those to indicate that they're known. We know v1 and v2. Those were given. And v1 prime was also given. The only thing that's not given is v2 prime, the unknown final momentum of the second object, which we can easily find by solving this equation. The algebra of solving this equation is simple enough. We subtract the m1 v1 prime from both sides, then divide by the coefficient m2 of v2 prime to get this. We substitute our values, noting that this is the initial momentum of the first object, the initial momentum of the second, minus the final momentum of the first. We get our 72 kilogram meter per second initial momentum of the first, minus the, or plus the negative 120 kilogram meter per second initial momentum of the second. And then this is really what we get by subtracting the final momentum of the first object, divided by the 15 kilograms and in a very straightforward manner we get our 1.2 meters per second.